Welcome to the Spoolwork solution of question 4.2 from the FEEG1003 workbook. So this is a dimensional analysis question. Question 4.2 is quite neat. It's a fairly simple question. It's fairly easy to solve, but the whole question involves sort of the full suite of, I guess, what dimensional analysis is really about. So it's quite a good one that you can apply the same techniques to then solve more difficult problems in the workbook. So we'll start off, as we always do, solving a problem. Read the question carefully, underline all the important bits, specifically the variables, and also what the question is actually asking you to do. So we've got 3 lines, some letters and some numbers. Let's pull out a highlighter. So we've got a parameter here, the velocity of ocean waves, v. Okay, it depends on the wavelength, so that's a length of a wave, gamma, and the acceleration due to gravity, g. We know what g is, so we'll just highlight that. So just write down the dimensions, so it's already given us the first little bit to do, and find the appropriate non-dimensional group. So we need to do that bit, write dimensions, and find the non-dimensional group. And then I guess what you would say the larger part of the question, if this was to be like a marked assessed question, what would the velocity and period of a kinematically similar wave at 1/16th scale? So you need to find out the velocity and the period. Okay, right. So the next stage is usually to draw a diagram. However, with dimensional analysis, it's a bit diagram light in that we don't really need to do it to understand the problem. What we should really do is write down the variables and their fundamental dimensions, which is actually what the question asks us to do to start with. So we'll start with that and we'll go straight over to the board now, and then I'll talk you through how we solve this problem. Okay, so we'll start off by doing the first part of the question, which is to write out the variables with their fundamental dimensions. Right, so they're the variables that are given to us in the question, and we've been told, it's implied in the question, that they form a dimensionless group. So based on the description of the problem, and looking at those variables, if we've got a little bit of experience in engineering, we can easily see that that will form, or we know it will form a dimensionless group, because we can do Buckingham pi, or the Rayleigh method, to achieve that. But looking at that, we kind of know that we're aiming for the Froude number, if I was to give you a huge, massive hint on what the answer is. So if you've not already done so, if you're one of my civil engineering students, then you'll have had a tutorial session on dimensional analysis where I give you hints and tips on how to do it most effectively. If you're not, go onto YouTube where you found this video, search for the module code FEEG1003, you'll pick up my user account, Luke Myers, click on that and you'll find a 50-minute presentation with some problems and some examples of what dimensional analysis is, what we use it for, and how to do it. Okay, so we can do 2 ways. We can do it the Rayleigh method, which is a sort of a quick, easy way for short problems like this. I've not taught that to anyone, but if you just Google the Rayleigh method or search for it, you'll see it's quite a quick way of doing dimensional analysis. I'll do the full Buckingham pi on this just because it gives us an interesting outcome, and we can learn a bit as we go. Okay, so we've got 3 parameters, Vg and this wavelength, and we've got 2 fundamental dimensions. 3 minus 2 is 1, so this will give us one dimensionless group, which is kind of implied in the question. Now we need to choose fixed and repeating variables. It's only one group, but obviously the purpose is with the repeating variables you raise them to a power, and for the fixed variables you don't raise them to a power. So again, going back to my tutorial / lecture, the best way to choose repeating variables is to make sure they're easily measurable, and the group of repeating variables has to include all of the fundamental dimensions in the problem. So looking at this, velocity and wavelength seem to me to be the easiest ones to measure. So we'll call those the repeating variables. We'll call G the fixed variable in this case, because measuring the acceleration of something is obviously far more difficult than velocity, but both of them have the same dimensions in. Okay, so we'll write just the standard Buckingham pi nice and carefully. So V and that one, whatever it's called in Greek language, I always forget because I can't be bothered to remember, equals length times -1. So there's velocity, here's the wavelength, and then here's G. Okay, and now we equate the powers. So for length, 0 equals A1 plus B1 plus 1. And the same for time, we've got 0 equals minus A1. So we've got time to the -1 to the power of A1, and then -2 there. Okay, these first two steps are the ones to take very carefully when we're actually doing it, after we've chosen the repeating and the fixed variables. So from that, A1 equals 1, U1 equals -2, and we end up with the following dimensionless group. Okay, it's interesting when we do it this way because we end up with not quite the Froude number. If you remember what I taught you before, we can do various things to manipulate these dimensionless groups. Remember that the fundamental dimensions on this fraction on the numerator and denominator must be the same, because this has no dimensions. Okay? So what we can do is we can square root the top and the bottom, and also then invert it. Okay? Both actions won't change the fact that this is dimensionless, because we've done exactly the same things equitatively, equally. Okay, so this is the form that civil engineers usually see the Froude number for open channel flow. V over root G times D, where D is usually the depth of the flow. But in this case, we've got another parameter, which is also a length or a distance, which is the wavelength. Okay, so dimensionally, it is equivalent. Okay, so that's the first part of the question done. Now, the second part talks about similarity between a big thing and a little thing, and this is what we use dimensional analysis and scaling for in engineering. So we've got a problem, I forget now, but something about wave impacts on a jetty or a pile, something in the water. So the idea is that we can keep the Froude number, this parameter here, the same in the big thing and the little thing. So we can do some testing in a flume tank, in a wave basin, at a smaller scale, keeping the same Froude number, because that will give us the same flow conditions, same kinematic conditions for the small thing. Then we can take the numbers from the small thing, it might be force, it might be speed, it might be distance, and then we can scale it up to the big thing. Okay, so we can do all of our testing under controlled, affordable conditions, and then we make the big thing. Okay, this applies to all other aspects of engineering as well. An interesting aero example would be the Avro Arrow, which was a Canadian plane which went straight to prototype. So what they did was they made scale versions of wings and fuselages, mounted them to rockets, and fired them into Lake Ontario. And from the data they obtained from the scale models and stuff they did in the wind tunnels, they went straight to manufacturing the first prototype of the plane. Obviously, when you've got a military aircraft, an interceptor capable of Mach 2, which was very fast when it was designed and constructed, you don't want failures of your big thing. In the same way, in civil engineering, you don't want the Burj Khalifa to start wobbling uncontrollably at the top and fracture and fail. You want so you can't afford to make things at big scale, see them fail, and then improve them. So that's all what sort of scale testing is about. So we need Froude number parity. So we take the velocity and the wavelength of the large thing, and then scale those conditions down to a small thing, keeping the same Froude number. Now the constant we have here, or we assume we have, is g, so the acceleration due to gravity. Okay, we're assuming that we're going to do everything on planet Earth where g is constant. Okay, if we're in a region where g is constant. So what we can write is Froude number in the model equals Froude number in the prototype or the large system, full-scale system. G cancels out on both sides, so we can write a ratio of velocities and a ratio of this wavelength. So Vp over Vm, so the prototype over the model. Oh, sorry, it's the other way around. Is equal to that. Okay, that's just saying that Froude here equals Froude here. Okay, so you can write out the things in full with the subscripts M and P. And then we have that as well. Okay, so we can punch in the numbers based on the question. And in the question, it gives us the scale factor. Now, when we talk about scale factors, it almost always refers to a geometric scale factor. So if our model is 1/50th scale, it means that the model is 50 times smaller than the prototype. So 50 times smaller than full scale. So here we're given a scale of 1/16th. So this value in here is 1, this value is 16. So the velocity ratio, so the velocity in the model compared to the prototype is going to be smaller because it's a smaller system. We've scaled it down. So we take the square root of 16, which is what the question gives us, or square root of 1 over 16, sorry, we get 1/4. Okay, so the velocity in the model is 1/4 that of the velocity in the full scale. And then the last part of the question talks about the period, so that's the time scale. So the period t equals the wavelength over the velocity. It's dimensionally the same. Length times the -1, length. Equate the dimensions, it's the same. So you can write the same thing out again based on the model and the prototype, and you end up with 1/16th times 4 for this. And so you end up again with an answer of 1/4. So the period of the model is 1/4 that of the full scale. Okay, so that's all what it's about. So when you get through, you've done your Buckingham Pi, Rayleigh method, whatever it might be, you got through to the final bit. Usually then the question asks you to go and do something with it. And that's what you do. You try and keep parity between these non-dimensional groups, between the big thing and the small thing. Okay, and all you end up doing is just putting the small thing equals the big thing, write out the equation in full with all the subscripts, look what might cancel, in which case gravity or density of fluid is another one, or viscosity, because you might be doing the tests in the same fluid at the large scale and the small scale. So some of these variables will cancel out, so you'll end up with scale factors of things like velocities, lengths, forces, etc. Okay, so all of the techniques here are the same as for a more involved question. It's just that you might have more of this to do, more bucking and pie, more groups, more manipulation, and then there might be a little bit more involved maths, but you can still get back to this. The conditions have to be geometrically, kinematically, or dynamically similar in the big thing and the small thing. Great, we're all done.